Good morning, students. Today we will start our next topic, that is the bond characteristic or the parameters. Before that, students, in our last class we have discussed the types of covalent bond, sigma and pi, how they are formed, and what's the difference between a sigma bond and pi bond. I have asked you to just point out the difference between sigma and pi bond. If you haven't, then just listen to me carefully. Now, the sigma bond is formed by the head-to-head overlapping or end-to-end overlapping, whereas the pi bond is formed by the lateral overlapping, that is called as sideways overlapping. Now, second point of difference is that the sigma bond, it can be formed between the s orbitals, that is s and s. It can be formed between a s and a p orbital, that is sp overlapping. And the third is it can be formed between the p to p orbitals, that is p and p orbitals. Whereas the pi bond has got a limitation that it is formed only with the p orbitals. It cannot be formed by the s orbitals. Third is that a sigma bond is a basic bond, right? It is not going to depend on the formation of any other bond, right? It is formed at the initial stage, whereas a pi bond is formed only when the sigma bond has been formed. That is, the first a sigma bond will be formed, and then only a pi bond formation can take place. The next point of difference is that the sigma bond, the extent of overlapping is maximum, and hence the strength of a bond is going to be greater. Whereas pi bond, in comparison to the sigma bond, the extent of overlapping is less, and hence its strength is also less. In sigma bond, students, the is evenly distributed, or electron cloud is symmetrical, right? Along the internuclear axis, it is symmetrical, whereas in pi bond, it is unsymmetrical and it is distributed up and below the plane, right, students? So the sigma bond, there can be the rotation around the bond, right? Because it's an end and end overlapping. So rotation is possible. Whereas in pi bond, the rotation is not possible. So if you can just see, remember that the pi bond, the p orbital, both the lobes of the p orbitals involved in the bond formation, they just lock with one another, or we can say they overlap with one another. So if the rotation occurs around the bond, what will happen? The overlapping will destroy, and hence the bond is going to break down. The students, just don't forget to point out the difference between the sigma and pi bond in your notebook, and please maintain your notebook properly. Now we are going to start the next topic, that is the bond characteristics. Student, once the bond is being formed, right, we have gone through that a covalent bond formation is taking place by the overlapping of the valential atomic orbitals. Now, once it has been formed, we have to discuss what are the characteristics which is required to define that bond, or what are the features of a bond, or we can simply say it to be the bond parameters. So, students, the bond parameters are bond length, bond order, bond enthalpy, and the bond angle. So, we will discuss them one by one. So, first we will start with the bond length, right? So, the bond parameters, there is bond length, then there is bond enthalpy, then there is bond angle, and then we have bond order, right? These are the four bond parameters. So first we will start with the bond length. Now, student, what is a bond length? So we have gone through in the beginning that whenever the two atoms approaches, right? So what happens that whenever the two atoms are approaching, the potential energy of the two atoms while they approach to one another, it is going to decrease, right? And they reaches at a equilibrium distance, a distance where the force of attraction and the force of repulsion balances and a bond is being formed. Now if further closer the atoms will come, what will happen? The repulsive forces will dominate and the bond will break down as the potential energy of the system is going to rise up. So here, what is the bond length? We will say that it is the equilibrium distance between two bonded atoms, right? So we can say it's the equilibrium distance between the two bonded atom in a molecule, right? So if it is a we can say if it is an ionic bond, right? That time it will be the ionic distance, right? And that will be the sum of the radius of the cation and the radius of the anion. That means I want to say here that if it is an ionic radius, that time it will be sum of radius of cation and radius of anion. And if it is a covalent radius, it is a covalent molecule, students here. Let me make it to be distance. This d ionic setting here, the equilibrium distance, or that is the bond length. In the same way, this is the covalent distance, or we can say the bond length of of a covalent bond when two atoms which are just linked through a covalent bond. The sharing of electron has taken place at that time, right? It will be the sum of the, we can say, the two atoms which are linked up. It is Ra plus Rb. That is going to be the covalent uh, distance, or we can say the bond length of a covalent molecule. Right now, the how has been the bond length being measured? Right, since the bonds are very the atoms are very small. So how the distance between the two nuclei of the atoms can be measured now? It is through the X-ray study, student. X-ray spectroscopic and electron diffraction studies that the bond length has been measured. Right, students? So what is a bond length, right? And how it is being measured? It is measured through the X-ray studies, right? The spectroscopic studies as well as the electron diffraction studies, right? So now comes how we are going to measure the bond length, right? So the bond length can be measured, or sorry, what is going to be the unit, right, in which we are going to measure the bond length. So generally, students, the Armstrong is used, right? So the unit of the distance, that is the bond length here, will be either in Armstrong, that is equals to 1 Armstrong will be equal to 10 to power minus 10 meter, and picometer, right, that is 1 picometer is equal to 10 is to power minus 12 meter, right? So the unit of the bond length is Armstrong, and it is picometer. Now students, there are certain factors on which a bond length is going to depend. Right? So we will next discuss here what are the factors on which a bond length is going to depend. Now students, I think the term bond length is clear that if this is the, we can say a covalent bond is formed, right? So this is the center of the nuclei. So this is going to be the bond length, right? So it is the distance, the equilibrium distance between the two nuclei of a bonded atom, right? And if it is a, we can say, ionic bond is formed, that time if this is a positive ion and this is the negative ion, then again this is going to be the bonding, right students? So now we are going to discuss the factors affecting bonding. Now students, what are the factors? The first one, the factor which is going to affect the bond length is the multiplicity. Okay, as I started with multiplicity, let me complete it. Multiplicity of bond. Now student, what do you mean by the multiplicity of a bond? The multiplicity of a bond here means that the two bonded atoms, how many shared electron pair is been present there. That means whether it is one electron pair, two or three, right? So if the number of bond is more between the two bonded atoms, then the bond length is going to be less, right? So here we'll, shorter is the bond length, if greater is the number of bonds between, now students here B slash W stands between, right? So number of bond between the two bonded atoms, right, in a molecule. So here, if it is same carbon and carbon here, so students here, since it is a single bond, the bond distance or the bond length of this bond is going to be greater than the double bond and the triple bond. So if just where does this bond single, double and triple occurs, we can simply consider to be the alkane, alkene and alkyne, right? So the bond length in the alkane is going to be more because here the two bonded atoms are held by a single bond, right student? Now this is the first factor on which it is going, the bond length is going to depend. Now the next factor is the size of the atom. Yes, so the size of atom, that is the second factor. The size of atom means here the atoms involved in the bond. Smaller the size of the atom involved in bond formation, shorter is the bond length. And the vice versa, or you can say that here it will also take place that if the size of the atoms are big which are involved in the bond formation, the bond distance or the bond length is going to be large, right? You can just, if we just consider here the distance between, this is a one atom of hydrogen, this is the another atom of hydrogen, right? This is the hydrogen molecule is being formed. Okay, let's see here that we have got two bonded atoms A and B, right? Now if the B atom is being replaced by some other atom which whose size is big, right? At that time, let it be in this way. So you can just find out easily that the this is A only and this is C. So here the bond length, that is between the two nuclei AB, is shorter since the size of the atoms involved in the bond formation is small, whereas the bond length is more when the size of the atoms involved, right, is big. That both the atoms will be big in size, then the bond length is going to be more bigger, right? And the third factor, student, is the hybridization. Though we haven't started it, right, we are going to discuss it in later classes later on. So third factor on which it is going to depend is the hybridization. So hybridization is the intermixing of the atomic orbitals. Okay, the third factor is the state of hybridization. Now, if greater is the involvement of the S character, right? So, if the S character involved is more in the hybridization, at that time the bond length is going to be shorter, right? So, greater is the S character, shorter is the bond length. Now, student, we have got mainly is Sp3 hybridization, Sp2 and Sp. Right? Here it is carbon-carbon, here it is double bond and here it is triple bond. Right? So the hybridization Sp3 has got greater S character. So here, sorry, huh? So here the Sp, that is S and P. Here the S character is going to be more of S. Now how many orbitals are involved here, students? 2. And out of that, complete one part is of the of S orbital. So if you just get it, you are getting how much? 50%. So student, here the Sp, we have got 50% S character is there, right? So that's why it has got the shorter bond length. So it will be in this way. So Sp3, so you can just predict what is the S character in Sp3. So it is 1 upon 4. Why we are getting 4 is 1 P3. So 1 plus 3. Total orbitals are 4, out of which 1 orbital is of S. So if you get it, it will be 25%. So here the S character involved in Sp3 hybridization is 25%. So that's why it has got less S character, right? Therefore, the bond length is going to be more. So students, just get this thing noted down. If any doubt, you can ask. Next, we are going to discuss the bond enthalpy. Now, what is the bond enthalpy? You know that whenever a bond is formed between the two atoms, the energy is getting released, right? As a result, the potential energy of the system or of the two bonded atoms gets lowered down, right? So, the reverse will also take place, right? That is, whenever the two bonded atoms are there, right, and the energy, when we give the energy which will be equal to that that is released when these two atoms were brought together, they form the bond. If that much amount of energy is given, the bond gets broken down, right? So bond enthalpy, it is the amount of energy which is given to break one mole of a bond of a particular type so as to separate the two atoms in their gaseous state, right? And the bond enthalpy is also known as bond dissociation enthalpy. So what is the bond enthalpy? So we are discussing this. So bond enthalpy, it is the amount of energy required to break 1 mole of bond of particular type so as to separate the bonded atoms into gaseous state. Right here, the two atoms will get separated individual in the gaseous state. The bond enthalpy is also known as bond dissociation enthalpy, and it is measured in kilojoule per mole, right? So I think definition is clear that if a bond to be formed, the energy is released, right? So that the potential energy of the state of the system gets lowered down. Similarly, when a bond is to be broken, the equal amount of energy is to be given, so that the two atoms which were earlier bonded, they get separated out, right? And they will be separated in their gaseous state. Clear? Now the second is that the bond enthalpy is also known as bond dissociation enthalpy, and it is measured in kilojoule per mole. Right, student? So yes, it's clear that kilojoule per mole. Next, we are going to discuss that what are the factors on which this bond enthalpy is going to depend. Student, the bond enthalpy will depend upon three factors, right? So the factors affecting bond enthalpy. The first factor is the size of the atoms. Now you know that now if the size of atom is big, what is going to be bigger? It will be bond length, right? So the bond length is going to be more. So if the bond length will be more, students, that time what will happen? The bond strength, that is the bond enthalpy, is going to be less, right? So we can say that here we will just write it in this way, that smaller the size of atom, that is shorter is the bond length, closer are the two atoms, right? And hence higher bond enthalpy, that means more amount of energy we have to give to separate them, right? High bond enthalpy, and Greater is the strength of bond. Is the strength of bond. Now students, the bond enthalpy, it is the measure of the strength of the bond. If the bond enthalpy will be high, the strength of the bond is also going to be high. The both depends directly on one another, right? That is related to the size of atom. If the size of atom is smaller, what will happen? The two atoms will be in the bonded state are going to be close to one another. That is, the bond length is going to be shorter, and hence it will be very difficult to get them separated, right? Hence, we will require more energy to break that bond, and therefore the strength or the stability of the bond is going to be high, right students? So next we will discuss the next factor which affect, that is the multiplicity of the bond. Now here the multiplicity of the bond is the second factor, which means that how many bonds are present between the two atoms in the bonded state. The second is the multiplicity of the bond, right? So if the multiplicity of the bond is high, that is the number of bonds between the two atoms is more, what will happen? They are going to be more closer to one another, right? And more energy will be required to break the individual bonds, right? So greater is the multiplicity of bond, multiplicity of bond, more energy is required to break each bond, and hence strength is high, right, if the multiple bonds are present, right? For example, if we take that we have got, this is O dash H bond students. So here the energy will be required to break the bond present between oxygen and hydrogen, right? There can be another example where we have oxygen with hold with other oxygen atom with double bond. This is the triple bond students. So you can easily predict that where the bond multiplicity of bond is high, definitely here the multiplicity of bond is high. Here it is 3, it is 2, it is 1 here. And second is that here the bond strength is going to be very high, right? So hence the bond enthalpies will be very high, and the molecule uh, compared to the oxygen, here the bond enthalpy is going to be high, right? And student, the third factor is the presence of lone pair. Lone pair on bonded atoms. Now here students, the both the atoms will be involved here. The lone pair of both the atoms will be involved here, right? When we discuss the strength of the bond, so the presence of lone pair on the bonded atom, right? So what does it mean? It means that if the lone pair will be present, then students, what will happen? There will be repulsion between the lone pair, and the bond will become that much weaker, right? So we can say that greater is the repulsion between the atoms, and hence less is the bond enthalpy, right students? Okay, now in the previous example where we discussed the multiplicity of bond, I have taken it was a nitrogen, triple bond nitrogen, because I am taking here the homoatomic molecules, right? I think is this clear? Nitrogen, what I am telling here. Just before this, we discussed the multiplicity effect of multiplicity of bond on the bond enthalpy. I have quoted an example of nitrogen molecule, oxygen molecule, and I have written here O dash S. Just get students replace it by hydrogen, that is H and H, because the previous two examples, that is oxygen and nitrogen, they are homoatomic. So here also I have taken it to be a homoatomic. So just get it corrected. Instead of O dash H, you will write down H dash H, that is hydrogen molecule, right? So we were discussing the presence of lone pair on the bonded atom. Now, if the lone pair is present on the bonded atom, students, what will happen? There will be repulsion, right, which will make the bond weak, and lesser will be the bond enthalpy. So the presence of lone pair on the bonded atoms causes the, you will just continue the statement, causes the repulsion between the bonded atoms, right? As a result, what will happen? As a result, bond enthalpy decreases, right? So bond enthalpy is going to decrease. Now here we will give the example where we will find that the lone pair on the molecules. Let us take example here, carbon and carbon. Right, here it is oxygen, or let us take in a sequence wise, carbon has no lone pair on it. Then we have coming to nitrogen and nitrogen, oxygen and oxygen, and fluorine and fluorine. Students, here the number of lone pair is 0, right? Here it is 1, here it is 2, here it is 3, right? I think this is clear that why 1, 2 and 3 have written here. It is the number of lone pair on each atom. So 0, 1, 2 and 3, it just denotes the number of lone pair on each atom, right? So carbon has got 1. You know that when you will draw the structure, Lewis structure, you will get a 1 lone pair on nitrogen atom. Similarly, you are going to get 2 lone pair on oxygen atom, and here on fluorine you will get 3 lone pair halogens. You will get 3 lone pair on fluorine. So here the bond enthalpy will be more of carbon, and it will be least for the fluorine molecule, right students? So you will just go through it. The bond enthalpy, or the bond dissociation enthalpy, will depend upon the size of atom, multiplicity, and the number of the lone pairs involved in the bond, right students? Get it noted down. Students, in our last class, we started the bond parameters, and we have discussed bond length and bond enthalpy. Today we are going to discuss one more bond parameter, that is the bond angle. Now, what is the bond angle? Whenever a bond is formed, right, either it is through the end-to-end overlapping, that is head-to-head overlapping, or the sideways overlapping, right, the electrons, the shared electron pairs are occupied in the molecular orbitals. Now, the angle between the two orbitals having the bond pair or the shared electron pair is known as the bond angle, right? So, we are going to do the next. The first parameter was bond length, second was bond enthalpy. Now, today we are discussing the bond angle. So what is the bond angle? It is the angle between the orbitals. Here should be two orbitals, right? between the two orbital containing the bond pair, right? Which is bond pair of electron. Now we will just try to understand it through an example here. Let us take an example of water here, right? So in H2O, the central atom is oxygen. This is the hydrogen, and this is another hydrogen atom. And we have come to know through the whisper theory that it has got a V or a bend shape, which is inverted V, a bend shape, right? So here the bond angle, it is this one between the two OH bond, and this line is indicating the bond which consists of the orbitals bearing the shared electron pair, right students? So here this is the bond angle here, 104.5 degree. In the same way, if we just draw the structure of the methane, here this angle, that is 109 degree 28 minute, this is the bond angle here, right? So I think this is clear. That is the angle between the two bonded atoms is known as the bond angle, and that angle is between the orbitals bearing the shared electron pair. Now, what is going? We can say that which factor is going to affect the bond angle, student? It is the presence of the lone pair on the central atom, or we can say the presence of the lone pair on the or around the central atom affects the bond angle, right? So if there will be more number of lone pair present, so what will happen? There will be repulsion more, so they will tend to just stay apart. As a result, they get distorted from the regular geometry. For example, the water in water, the expected geometry of water molecule is tetrahedral because it consists of 4 electron pair, right? But due to out of that 4 electron pair, 2 are the bond pair and 2 are the lone pair. The 2 lone pair are on the oxygen atom. So due to the repulsion being maximum between the lone pair and lone pair, the shape get distorted from the regular tetrahedral geometry to V shape or a bent shape. Right students? So the presence of the lone pair around the central atom affects the bond angle. Now student, after this we will discuss, this is about the bond angle, right? Now the next parameter is the bond order. Now students, what is a bond order? So bond order actually expresses the multiplicity of the bond, right? So the next parameter or the characteristic to define a bond is the bond order, right? It measures or expresses the multiplicity of a bond, of bonds between two atoms, right? Or we can say that it is the number of shared electron pair between two bonded atoms in a molecule. Greater is the bond order, greater is the number of bond order. I am expressing bond order to B dot O, that is bond order. Stronger is the bond and high bond enthalpy. Therefore, high stability. Right? For example, in alkane, you can see that in alkane, we have carbon and carbon single bond. But in alkene, we have double bond between the two carbon atoms, and in alkynes, we have triple bond in alkynes. Right? I think these are hydrocarbons, alkane, alkene, and alkyne. Alkene is the saturated hydrocarbon, whereas alkene and alkyne are unsaturated hydrocarbon. Here we have single bond, so the bond order here is 1, here the bond order is 2, and here the bond order is 3. So as the bond order will increase, what will happen? We will require more amount of heat to break the 1 mole of a bond of that particular type. Right? And hence greater will be the energy. So if energy will be higher, so the molecule will be stable. Till then, that moment we are available to provide that much amount of energy. So higher the bond order or greater is the bond order, we will have the higher stability of the molecule. Right, student? So hope so the last line is visible here to you all. Yes, it's visible. Now the next thing is that the bond order, it is a whole number, or we can say it's a complete number. 1, 2, here it is 1, here it is 2, here it is 3. Students, you should know that a bond order can even be a fractional also. Right. So this is the another point. And when you will do the MOT, that is the molecular orbital theory, that time you will come to know that how we are getting the bond order in fraction also. So the next point is that bond order can be fractional. Right? The bond order can be fractional. That means here n, or we can say it can be in fractional. It will be 2.5. Right? So it means that the covalent bond, right, is, or the multiplicity of the bond is in such a way that it is coming 2.5 of the covalent bond. Right, students? So here it will depend upon the number of the electrons which will be available both in the bonding and anti-bonding orbitals. We will discuss this later on in details. But till now you have to keep in mind that a bond order can have a fractional value also. Second thing is here that the isoelectronic species, that means which have got the same number of electrons, isoelectronic species will have same bond order. Students, if the number of electrons are equal, that is if it is an isoelectronic species, at that time the bond order is also going to be same. Right, student? So if we take, this is the fluorine molecule, right, and we have this, the oxygen molecule here. So if you see the fluorine molecule and the oxygen molecule, so here students, the number of electrons in fluorine molecule F2 will be how much? 9 is atomic number of single fluorine atom. So we have got 2 fluorine atom, that means 18 electrons here. And in oxygen, here we have got 8 atomic number, right? 8 to 16 plus 2, 18. So they are having in total 18 electrons. That means they are isoelectronic species. And the bond order of it comes to be 1. So if we know the bond order of one isoelectronic species, we can just predict the bond order of the other isoelectronic species if we know that these two have got the same electrons, right? So this is about the bond order. So greater the bond order, higher will be the, we can say greater is the bond order, higher is going to be the bond dissociation enthalpy, and hence stability of the molecule or of the bond is going to be high. Yes. So students, please get this thing noted down and go through it very carefully, because we are just going through this the basic unit of the chemistry, right? Here we are coming to know about the main fundamental concepts of the bonds, that what is a covalent bond. Generally till now, the sharing of electron pair taking place, we say it to be a covalent bond. That's a fine, but further more things are there which you have to learn, and these all are the new things which you are coming across. So just grasp them and just get it noted down in your notebook.